Presenting What's New in Word Vectors, please welcome Jerzy Kowalski.
Thank you all. Thank you, Kuba. I'm really glad to be here. And my name is Jerzy Kowalski. I'm Python developer at STX Next, and I'm also a machine learning fan. And today I want to talk about word vectors and current achievements in this area. And we will start with explaining what are word vectors, why do we really need them. Then we will see a most naive, simplistic way to implement them, just to grasp some intuition how they can be built. Then we'll move to real solutions that uses deep learning, and we'll see them in action during a demo. We'll end with a short summary, and as always, time for questions. I would like us to be able, after this presentation, to be able to answer this question. Can computers understand a text and answer questions about it? And I mean, at least at the level of 6-year-old kid. And before we move on, I would like to point out that I may use word vectors and word embedding interchangeably. So I'm just telling it to not get confused when I use word embedding. So you want to build some machine learning solution. First of all, you need to think how you will represent your data. And if your input data is text, you are dealing with natural language processing, NLP in shortcut. And you have a problem that is not such distinct in other areas when we can apply machine learning. Let's take a look at images, for example. They are just grids of numbers that are combined into color channels. And if we are dealing with sound, we can take advantage of spectrograms, which are just representation that shows us how different frequencies in signal vary over time. And this representation may be not perfect, but they describe respectively images and sound with numbers, and that's something what we like to have because machine learning algorithm needs numbers as an input. But what about words? We have a problem because computers don't understand the concept of words. We cannot just measure a word and use this measurement to create some numbers for it. So before even starting working with combining machine learning and text, we need to turn those words to some vectors so that we can use it as an input to our model. And let's start with the most simplistic way to do so. Let's assume for simplicity that our dictionary contains 4 words only. Word vectors are cool. Each such word will be represented by so-called one-hot vector. One-hot vector is just a sequence of zeros with single element that's value is 1. And each word will have a different one-hot vector. I think that this table depicts nicely how they are created. And now let's say you want to create a vector that represents whole sentence or even a whole document. So you can just add vector representation of separate words, add them element-wise, and you can get a vector like this one on the bottom of the slide. So the only missing one here is because we didn't use word vectors in here. And this representation is called bag of words. And you can see that it is a rather simple idea, which is nice because we can interpret it. And it can work quite well for some easy tasks. For example, document classification. If you got some data sets with text about, let's say, sports and cooking, you can turn those texts into a bag of word vectors and apply some machine learning solution that will be able, after training, to differentiate between them. But even we can represent a meaning of whole sentence or document, we are still missing a meaning of single words. Let's consider two synonyms. Their vectors will have nothing in common. So it is a problem for us. What is more, there are more problems for such naive solution for word vectors. For example, there are multiple words that appear in different contexts, like words like the, which, when, and if we, for example, get such classifier for sport versus cooking, it will add just a noise to our representation, which is no good. In real world examples, when our dictionary is huge, our vector size will be huge as well. And we don't know how to handle words that have never appeared during the training. There are some solutions to overcome these problems, and if you are curious about them, this presentation will be on my GitHub and will be published. So you can just click the links here and read about them. But we won't get into those details because we have another solution that uses deep learning and overcome these problems in a more natural way. And the first such solution that used deep learning for preparing vectors for words were word2vec. The first one, which in fact gained a huge popularity. And its high-level idea is really, really simple, because we can assume that if we got two words that are often surrounded by the same words, they probably may have similar meaning. Let's take a look at this example. I eat fresh apples from my garden, and fresh fruit are ready to eat. So both apples and fruit are surrounded by words eaten fresh. So it's kind of a signal that they may have something in common. And if we got lots of text, we can even train a neural net that will be able to tell us, given two words, what is the probability that they can be its neighbors. And before starting such training, each word is connected with some vector of weights, which is at the very beginning, it's totally random. But during training, during the process of net learning the task, it will change in a way that at the very end of a training, such vector of weights contains meaning of a word. What does it mean? So if we, for example, take vector for word apple and fruit from the example before, and we compare it with some standard way to compare distance between vectors, let's say dot product, it will be far shorter, the distance between those two words, that distance, for example, between vectors for word apple and computer. So we find a way to. Sorry?
Bad example, apple and computer.
Okay, yes, thank you for that. Okay, but not only we gained not only the meaning from this representation, but only a way to represent relations between words. Let's take a look here. If we visualize these vectors of words to two-dimensional plane and plot it like this, we can see that, for example, shift between queen and woman is the same like shift between king and man. So this representation learned that the queen is female counterpart of a king. Isn't it amazing? And if we ask our representation, hey, is the relation between London and England the same like between Paris and France? It will answer, yeah, sure. What is more, it even captures things like plural form, because, again, shift between dog and dogs is the same as shift between cat and cats. So we got a representation that not only can capture meaning, but also can capture representations. Relations, both semantical and grammatical one. And now we are moving to the newest solutions in this area that are younger than a year. And let's start with Elmo. Elmo is a shortcut for embeddings from language model. And its idea is to use words representation from some trained language model and then use this representation as an input for our custom model that can be shallow. What does it mean? It means that it don't have to be like gigantic deep neural net that we'll train for decades. And I know it may sound still sound like a Chinese to you, so let me break it up for little pieces. So first things first. What is a language model? So if you give a sequence of words, for example, the quick brown fox, the nicely trained language model should output jumps as the most probable next word which will appear after the sequence, the quick brown fox. It will also tell you that speaks is a word that is a little bit less probable, but it still does make sense because it is a verb. But we definitely don't want our language models to suggest a sequence like the quick brown fox Canada, because it is nonsense. And nice feature about Elmo language model that Elmo use is that it is character based. So it can handle words that it has never seen before during the training. For example, if we make a typo and ask our language model what is the next word for sequence the quick brown fox, it should answer exactly the same. And what is even more amazing about Elmo vectors is that their values depend on the context they appear on. So if we got word2vec in the previous slides, we used context only for training our vector representations. But now Elmo uses context also for prediction. So it allows us to differentiate between words that can have many different meanings. If it is still unclear to you, let's take a look at this example. He can type over 100 words per minute, and that guy is really not her type. If we used word2vec, both type words will be represented by exact same vector. But if we use Elmo, it will not be that case because their meaning are different and Elmo can capture it. So it is really nice. Now let's take a look at really high-level diagram of how Elmo architecture is organized. Like I said before, it is based on language models. So if sequence ends with brown, it should output fox. And this model is created by two main blocks. The first one, depicted as an orange block here, creates word embeddings out of characters. And the second one is the standard solution, modern solution for language models that is based on a recurrent neural network called LSTM. And we already have a word vector here because it's an output of a first block. But what is more, our language model has two hidden layers, and we can extract those hidden representations from it. And now we have three vectors per each word, which then we can combine in some way that fits our problem. Okay, so let's move on to current NLP emperor, and it is BERT. BERT stands for bidirectional encoder representation from transformers. And it again uses language models, but it uses it in a different way. Because now you add at the top of the language model some shallow neural net, and you retrain the entire model for your specific problem. So not only your shallow net, but you also retrain a language model. And for us developers, what is amazing about BERT is the thing that straight after its authors published a paper about it, they also open source code for it and gave us a pre-trained language model on, I don't know, billions of words, enormous data sets. So they really did an amazing job for NLP community. And one more thing that differs Elmo between BERT, apart of the color of the fur, is that they uses some different mechanisms to obtain language modeling. So we had LSTMs in Elmo, and in BERT we are taking advantage of models called transformers. Transformers are basically created again from two blocks, encoders that takes as input some sequence of words, create some numerical encoded representation, and decoders which take this numerical representation and give some output. Nice use case of transformers is translation, and they are proven to perform really well on that specific task. So authors of BERT decided to take encoders part of the transformers and create language model, which is called masked language model for this specific task. And the name masked language model comes from the process of the preprocessing of data before training. So we randomly pick 15% of our words from our training data set, and we replace them with a special token mask. Then, again, encoder, like in the example before, encodes words to some numerical representation, and then at the top of the language model, we have simple net that can classify words. So it can take this encoded representation and output what it think the word is. And during training, we only care about masked words. The second step of training of BERT language model is called two-sentence task. And we got as input two sentences separated by special token SEP, and the encoder part remain the same. We just change this yellow block here to binary classifier that will tell us whether the two sentences are consecutive ones or they are just random sentences. And it learns these tasks. And if we got pre-trained language model for BERT, we can replace yellow block with anything we want, and we can retrain it for our custom task. You want need spam classifier, just provide enough data, to change this yellow block to some binary classifier that will just output spam, not spam, and you are ready to go. Okay, so now it is time for demo, and I will show you how BERT tackles machine comprehension problem. And machine comprehension problem has two inputs. Let's say paragraph of text, and question asked in some natural way. So, for example, we got entry about BERT from Wikipedia, and we ask who was the first BERT performer. And what the model should do is to find a piece of original text that answers this question. It is really important. The answer has to be in a text, and we train a model to find it. And a standard data set to do such thing is a Stanford question answering data set, which is based on Wikipedia entries. Okay, so basically I downloaded the pre-trained model for language for BERT language model, trained it on the Squad dataset for machine comprehension, and wrapped over a simple web server to show you results. So we can run it, and we will be using Postman, nice desktop app to send a request to the web server and get an answer in some human readable, user-friendly way. So let's see if the, yeah, it has started. And we have got a Wikipedia entry about Bert, just like on the slides. So Bert is a yellow Muppet character on the long-running children's television show Sesame Street. Bert was originally performed by Frank Oz. Since 1997, Muppeter Eric Jacobson has been phased in as Bert's primary performer. Blah, 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 blah. Who was the first Bert performer? Tell me, Bert. Okay. Can you see this screen? Is the font okay? Frank Oz. So that did it perfectly. And please notice that it's not simple matching of, for example, okay, I saw who, so let's search for some people here, because there is Bert, there is Eric Jacobson, and there is Frank Oz. And what is more, in the sentence with Eric Jacobson, a word primary appear, which could be misleading even for some human to understand what happened. And Bert deal with it greatly. And you know, Bert was trained on Wikipedia, so the authors of it claim that it even can beat human on this task. But if I saw it first time, I just wondered, okay, but is it able to at least answer some simple reading comprehension task that you will give to some 6-year-old kid? So I just Googled for things like that. Okay, A1 reading comprehension PDF. Okay. And I got some, okay, let it load. I got some text about Mary and her family, pets, and so on and so forth. Fortunately, we don't have to read it because we've got a key for it. Okay, can you see it, or should I make it a little bit bigger? Okay, is it okay right now? Okay, so let's start with simple question. How old is Mary? Oh, sorry, just hidden. And it answers 10. We can answer, how does Mary's hair look like? And we know that they are long and brown. Send it to Bert. Long and brown. And we can even answer some more tricky questions. For example, let's take a look here. We get Tiny. It's a hamster of Peter. So let's ask who owns Tiny? Oh, okay. It captures. Okay, so yeah, it is also typo proof, but it wasn't intended. Okay, so let's get back to the presentation.
Can we challenge it?
Yeah, we can, of course. Yeah, give it to me. It is not perfect, but
I don't have the question. I think there are wiser people here. So
I have one question for the first one. Could you switch the questions around so you get, was it Bert back as the answer? So the first question was that who performed Bert, but could you switch it around so that which Muppet character was performed by?
it's Sesame Street. Okay, I can try it. It will be the first time. Which Sesame Street character was performed by Frank Oz? I'm curious. Bert, woo! Okay, so let's move on. Code for this simple web server is on my GitHub, as well as trained model for machine comprehension, so you don't need to train anything. You can just download it and play with it if you want. And the presentation will be there. It is there as well, I think. Okay, so let's sum it up. First of all, what's wrong with those NLP guys? Elmo, Bird, who is next? Cookie Monster or Big Bird? I don't know, but it will be really exciting new model which will beat Bird. And we can say that traditional word vectors have numerous of flaws, but they can be used successfully for some simple tasks. But thanks to deep learning, we are really able to capture a meaning of words with numerical representation. Current state of the art solutions are based on language models, like Elmo and Bird, and now we need less data and simple models to do amazing NLP solutions now, because we mainly need just those yellow blocks at the very top. So the things go really nice in the last year for NLP, and you can read about them on some blog posts, and you can even read some papers about it. And now it's time, I think, 4 minutes. I have it here on questions. If you got any, I'm here to ask you.
Well, first of all, a big round of applause for Jerzy.
Thank you.
This presentation brought to you by the letter O. Okay, we have time for exactly one question. We have 1.5 minutes. Let's go. Make it a short one, please.
Thanks, cool presentation.
Thanks.
I really wish I could have something like that when I was in high school back in the day. It would really make my life easier. But anyways, I was wondering about this text about Mary and her pets.
Yep.
Although I did catch your remark that it only answers when the actual answer is in the text. But I was wondering what could happen if you asked a tricky question like, who owns, and you insert here the name of the pet that isn't in the text. Like, for example, who owns the turtle, for example.
Do
what
we have
would
a time
actually
for
happen?
Such...
Well, let's see. We still need the time for Maciej Urbański to get his microphone. So if we could grab him and he'll be getting his microphone, you can answer in the meantime. Yeah, sure, go.
Oh, okay.
Because I was actually interested in whether it would throw some error or
Okay,
maybe somehow...
Give me just a question. No, it won't be an error. It probably answer Mary, because text is mainly about Mary, and if he doesn't know what to answer, he answer Mary, maybe. So what was the exact your question? Who owns?
So, who owns a turtle?
Turtle. Pat and Fluffy. Okay.
I mean, some answer is better than no answer, I guess. But
Yeah.
Thanks.
Okay.
Okay, thank you.
Thank you.
I think we should be finishing here. Another... I'm sorry?
You said it can answer in multiple languages. Could you ask in Polish? Would it...
Not this model, but you there are birds trained for on Polish data sets, but it's not this case. But yeah, you can do it.
And thank you. Question, answer, full stop. And another big round of applause for Jerzy.